So let's look at what we call the alkynes. This is the third group of the hydrocarbons that we are looking at, but this is not the last group of the carbon compounds to look at. We shall look at alcohols, we shall look at carboxylic acids as the other organic compounds that we shall look at in organic chemistry. So what are these alkynes? What makes them special? How do we prepare them? How do we use them? What are the chemical reactions with them? How do we name them? Those are the things that we are going to look at in this session. Okay, there are quite many things, right? But I can guarantee that they are actually very simple concepts to basically understand. So let's start. When we talk about alkynes, please remember that we are talking about compounds that have triple bond, at least a triple bond there. So we should be having triple bonds between carbon and carbon. Okay, that's one of the key things that identifies the alkynes, right? Yes. They have this general formula, and like what we have been previously doing is that there is always that n, and you can assume n to be anything. It can be n is equal to 4. If n is equal to 4, what will you have as the alkyne? What alkyne will you have? So if n is equal to 4, with our general formula of n CnH2n minus 2, so if we assume that n is 4, you will have C4, this will be H2n, that will be 8, because it is 2 times 4, right? To get that 8 minus 2, so you will basically have C4H6, right? Yeah, so let us see what comes out of this. Remember, each carbon atom must be bonded to at least 4. So you should have 4 bonds there. So the first rule is that at least you should have the triple bond, and then the other carbon atom, and another carbon atom, because we are referring to 4 of them, right? So let's make sure that we have at least 4 for each. So this one has 4, this circle one has 4 bonds, 1, 2, 3, 4. This one also has 4, the second one has 4, the third one has 4 already, and then this one needs 3 more to make 4. Okay? So how many hydrogen atoms do we have? Yeah, so let's count. This is 1, 2, 3. This one will not have because it is full. This one will not have because it is full. 3, 4, 5, 6. Does it come out? Yes. You can see that. So it is C4H6, right? That is what we have just found out. If the n is equal to 4. What is the name of this compound? I guess you know that it is 4-but comes in, and then you add that suffix. For alkynes, the suffix is this that you add. It's this one. YNE. YNE is the suffix that you add. So but for butane, right? It's this one down here. Yes, that's the one. So here, butane. Okay. What is the unique thing with this one according to what we had just written here? What's the difference? The difference is in indicating the position of the triple bond. So the position of the triple bond here is at carbon 2. Okay, carbon 2. And here, but1 is indicating that the triple bond is at carbon 1. That's what concept is that? That is the concept of isomerism, positional isomerism, right? Yes. So that is something that you can note there. So butane, propane, and then which other one? Okay, and we talked about ethane, right? Yes. So ethane will be 2, propane will be 3, butane with 4 carbon atoms, right? Yes. So how do we name them? The same rules apply. The same rules apply. Okay. About the suffix. In this case, for alkynes, it's YNE. That replaces the E for the alkenes, right? Yes. So instead of having ethene, we are now having ethane, right? You see this? You see that? That's what we are talking about here and there. And then you can always indicate the number of the carbon atom where the triple bond is located, just like here. Here you don't indicate the number because regardless of whether you put the double bond here or here, the position will be 1. That's why we only start with the number at butane. Isomerism, I think we have explained it. You can have the same compound, the same alkyne in this case. Okay, so let us use this example of butane. Go back to this example. You see that we placed the triple bond in the middle, but you can change where that triple bond is. Let's just draw it here for clarity. So we had 1 carbon, 2, 3, and 4, because we're talking about butane, right? Yes. So you can place the triple bond there. You can place it here, or you can place it here. Okay, you can place it, or you have option 1, option 2, you also have option 3. And if that means that you will have the same compound, but the position of the triple bond will be different. And that is basically the concept of isomerism. Okay? So the more you have many carbon atoms, definitely you have increasing molecular mass because of that. But the more you have a long chain, the more likely you will have different varieties. You have more options to place the triple bond. And even the arrangement of other groups that can be branching from the main chain. Okay? Yeah. So isomerism in alkynes can be positional or can be branching isomerism. How do we prepare alkynes? For example, if ethane actually, you can use calcium carbide and water. The reaction between calcium carbide and water is what will give you ethane. Okay, so what you do, you need to have some sand in there. The sand, we shall look at it later on, just shortly. But you just have calcium carbide in there, add some water dropwise, and then you will see a gas that will be emitted from here and to be collected over water. This is basically to say it is not soluble in water, okay? So that's why you can collect it up here. It's also less dense than water, right? Yes. So why do we use the sand? This reaction between calcium carbide and water gives us a lot of heat, and therefore we need to make sure that that heat does not cause cracking of the flask. Okay, so when we have some sand, it helps in absorbing some of the heat and distributing it uniformly. This helps make sure that the reaction does not overheat it, leading to the breakage of the glass flask. So that's why we have sand in there. So in our equation for reaction of calcium carbide with water, the sand is not there because it is not actually a reactant. It is not involved in the reaction, for it just absorbs the heat. Okay, that's the point there. So, like I've already said, less denser than air, right? Because that is why we are collecting with what we call the downward displacement of water, right? And then it is insoluble in water, that's why we collect it over water. Okay? Like also like the alkenes, there are some features that are related to the size of the alkyne. So issues to do with boiling and melting point, they all increase according to the increase in molecular size, right? And then the first 3 alkynes are gases, then we also move to liquids, and then those that have more than 15 carbon atoms are actually solids at room temperature. Okay. What reactions do we have? One keynote is that they are not as reactive as the alkenes. Okay. So if you remember, we started with the alkanes, they are not very reactive. And then we came to the alkenes, we said they are more reactive than the alkanes. Now we are moving to the third group, which are the alkynes. And we are saying for them, they are not actually as reactive as the alkenes. So meaning that the alkenes are more reactive. Okay. So what are the reactions that the alkynes actually are involved in? Hydrogenation, addition of hydrogen atoms, right? Hydrogen. No, just a minute. The first reaction of the alkenes that we are going to look at is the reaction with the halogens. Halogens include chlorine, include iodine, include bromine. So in this case, we are using the reaction with the bromine, what we call bromine water. So what happens is that the reaction of alkynes with bromine water is that decolorizes this to a colorless solution. But that reaction is what we call an addition reaction. Okay. Also remember, in the alkenes, you have what we call addition reactions. So the reaction between bromine, which is a halogen, with alkynes, okay, which in this case we are saying ethine, that reaction is an addition reaction, and we can also call it halogenation reaction. Okay, it decolorizes the bromine water. That's the reaction in there. The second reaction is hydrogenation, addition of hydrogen. Okay, when hydrogen is being added, we lose the bonds. Remember, we have triple bonds. So we add hydrogen, we lose the one bond, and then we form alkene. So we add more hydrogen, then we form alkanes. Okay, so hydrogenation is also an addition reaction. It's just like you just add more hydrogen to it and then balance the equation, and that's it. The conditions, usually there should be a catalyst at least, and then the temperature also matters. For ethine reacting with nitrogen, you will need nickel or nickel as the catalyst in there. High pressure, high temperature. And then you can also form what we are calling here partial hydrogenation, that you're not replacing, you're not adding all the hydrogen there. Okay, and this happens if you keep the room temperature, you keep the temperature at room temperature. Combustion, still you can produce carbon monoxide with limited oxygen, but you can also produce carbon dioxide when there is plenty of oxygen. Okay, so this is the equation that we have put there for complete conversion. Okay, so when do we use alkenes? Alkenes are used in preparing a number of solvents. For example, preparation of organic solvents, preparation of ethanoic acid, acrylic acid, ethanol, and then the pipes that are connected to your homes. Those pipes are actually made. If you check them out, they will have this PVC. Those are polyvinyl chloride. That stands for polyvinyl chloride. That the material that is used to make these pipes that I'm talking about, they're actually made from alkynes. Alkynes play an important role there. Remember, the alkenes play an important role in crop ripening, in fruit ripening, right? Now here we're also talking about ethine playing an important role in ripening, okay, ripening of fruits and also preserving them. And then it being used in lamps, acetylene is used in lamps, and then also the plastics are also made from this alkyne. The end of this presentation, where we have looked at the last group of the hydrocarbons, and that group is what we call the alkynes. The alkynes are unique because they have triple bonds. Okay, but the presence of this triple bond does not necessarily make them as reactive as the alkenes. Okay, and we have just emphasized that ethine is actually can be prepared in the lab using calcium carbide. There should be sun there and also water. So the water reacts with calcium carbide from calcium hydroxide and the ethine. Okay, and we have just noted that ethine can be used, or alkynes can be used in a number of processes. Thank you.